Welcome to the second session on ionic equilibrium. In this session, we will be dealing with acids and bases and theories defining acids and bases. So, let us move on. We know what is an acid. Acid is any substance that has got sour taste and it reacts with bases to give salts. Such things we call them acids. Besides, it turns the blue litmus red. Then we have another class known as base. Base is any substance that has got a soapy feel, it has got a sour taste, and also they react with acids to give salts. Besides, they also turn the red litmus blue. So, these are the things we have seen in lower classes, and this is what we say about what is an acid and a base in general. Now, let us see some of the theories which define what do you mean by an acid and what do you mean by a base. So, first one is the Arrhenius theory of acids and bases. In Arrhenius theory, he defines acids as a substance which can furnish H plus ions when dissolved in water, and thereby it increases the concentration of H plus ions in the solution. So, acid is any substance that increases the H plus ion concentration in a solution. Now, for example, let us see the acid HCl. So, when we take HCl and AQ represents that HCl is in the aqueous state. It furnishes H plus ions in the aqueous medium as well as Cl minus ions. And actually this H plus ions, as you all know, it is a single proton and it won't exist as H plus, but just for the theory's sake we have put it as H plus. That will be in the hydrated state where H plus takes up a water molecule and gets converted into H3O plus ion, and that is how it exists in aqueous solution. Now, when we come to base, base is a substance that furnishes OH minus ions when dissolved in water, and thereby it increases the concentration of OH minus ions in the solution. For example, let us take a base NaOH, aqueous again represents it is in the liquid, dissolved in water, gives Na plus in aqueous state plus OH minus ions. So, an alkali or a base is a substance that increases the concentration of OH minus ions in the solution, because when we dissolve NaOH in water, you have an excess of OH minus ions in the solution. Next, let us see what do you mean by a neutralization reaction. Neutralization reaction is actually a combination or a reaction between an acid and a base. An acid reacts with base to give salt and water. Now, this reaction we call as a neutralization reaction. Now, according to Arrhenius concept, this is actually a combination of H plus ions in the aqueous medium and OH minus ions to give water. Okay, this is true because it has been found that the molar heat of neutralization of all strong acids and strong bases, they are equal to minus 57 kilojoules per mole. Okay, so when 1 mole of H plus ion and 1 mole of OH minus ion combine to form a water molecule, that will be, it will giving 1 mole of water, and the value of energy released will be minus 57 kilojoules. And this value, in the case of if we take either acid is weak, the acid is weak, or if the base is weak, or if both are weak, in both all these conditions, the value will be less than minus 57 kilojoules, or you can say that do not take the sign, it will be numerically less than 57, that is it can give a value like minus 56 or minus 53, and this minus stands for do not take it as a negative sign, it shows that the energy is being released per mole. Okay, this is because some of the energy has been utilized, because weak acid and weak bases, they do not combine readily because they are not completely ionized, and therefore some energy has been utilized to dissociate the weak acid or the weak base, and then only they get the ions in order to combine to form 1 mole of water, and therefore the value will be less than minus 57 kilojoules per mole. Okay. Now, we are going to consider what type of acids and bases we have. We can classify acids and bases as their strong acids and bases and also weak acids and bases. Strong acids and bases are those which are completely ionized in their aqueous solution. They are completely ionized, whereas weak bases, they are not completely dissociated or ionized to give their ions. They are only partially ionized. Such acids and bases are considered as weak acids and weak bases. Now, let us see some of the examples. Strong acids are those, for example, HCl, nitric acid, sulfuric acid, etc. Strong bases are, you can have both alkali metal and alkaline earth metal hydroxides, that is some of the examples I have written as NaOH and KOH. Weak acids, usually they are acetic acid, hydrogen cyanide, boric acid, oxalic acid, etc. and weak bases are aniline, ammonium hydroxide, aluminum hydroxide, etc. They are all weak bases. So, these they do not ionize completely, while these are completely ionized. Completely ionized. These are only partially ionized. Okay. Now, let us see what are the limitations of Arrhenius theory. They are applicable only for aqueous solutions. You can apply this only in aqueous solution, cannot be used for many acid base reactions which occur in a non-aqueous medium. Okay. And again, it fails to explain the acidic and basic characters of substances which cannot furnish H plus ions and OH minus ions. We have many substances which do not furnish H plus or OH minus ions, and still they can be either acid or a base. So, these are the limitations of Arrhenius theory. Now, we have another theory known as Lowry-Bronsted theory of acids and bases. In this theory, an acid is defined as a substance which has got a tendency to donate a proton. It has got a tendency to donate a proton, that is enough, and that will be a acid. Because in the other case, Arrhenius theory, you have to put it in an aqueous media, and if they furnish H plus ions. It is not the case here in this. If acid is a substance which has got a tendency to donate a proton, that is enough, we need not apply it into an aqueous solution. And base is a substance that has tendency to accept a proton. So, acid donates a proton and base accepts a proton. So, you can call acid as a proton donor while base as a proton acceptor. Now, let us see an example. We all know HNO3 is an acid, and when HNO3 is treated with water, this HNO3, this donates a proton to water. It is donating a proton to water, and water changes as H3O plus. And after removing H plus ion, what is left out will be an NO3 minus ion. Now, let us see, this is an acid according to Lowry-Bronsted theory, because it donates a proton. Since water accepts a proton, this will be a base. Okay. Now, here you can see you have an ion H3O plus, and this ion is capable of donating a proton, because H3O plus can donate a proton and it changes to water molecule. Okay. So, H3O plus which is capable of donating a proton according to Laurie-Bronsted concept, that will be an acid. But we will not call that as acid because it comes from nitric acid, the H plus ion, water acquired it from nitric acid, and so it gets H3O plus which is an acid, and this acid is known as a conjugate acid. We do not call that to be simply acid, this is considered as conjugate acid, and this conjugate acid is formed from water which accepts a proton from nitric acid. Okay. In a similar way, the nitrate ion, it can accept a proton and get converted into HNO3, and that is the nitric acid. So, here nitrate ion which is capable of accepting a proton, this will be a base, we will name that to be a conjugate base. And this is a conjugate base formed from nitric acid by donating a proton to water. Okay. So, this will be a conjugate base, this is called. Now, what is the difference between a conjugate acid and a conjugate base? Just note that here they differ by a proton. You just watch, you take water and its this conjugate base and its conjugate acid, it differs by a proton H plus. You take nitric acid and its conjugate base NO3 minus, they differ by a proton H plus. So, that will be a difference between a conjugate pair, you can call that to be an acid and its conjugate base, a base and its conjugate acid. Now, let us take the example of ammonia. When ammonia which is in the gaseous state added to, or you take liquid ammonia, liquefied ammonia, you add it to water, you will get actually ammonium hydroxide in which NH4 plus and OH minus ions are present. What happens is that ammonia takes up a proton from water. So, ammonia accepts a proton and gets converted into ammonium ion. Water loses a proton and gets converted into OH minus ion, just like in the previous case. So, ammonia will be the base, water is acting as an acid, and ammonium ion which is capable of donating a proton will be a conjugate acid, and OH minus ion which can accept a proton will be the conjugate base. Hope it is clear. And now you can see in both cases you have an equilibrium, because in the first case acid and base, they react to give a conjugate acid and a conjugate base which can react back and give back an acid and a base. So, we consider in this concept that is there is an equilibrium existing between these two. Okay. Now, let us go to the conjugate acid and the conjugate base pairs. When HCl is added to water, you are having H3O plus and Cl minus. HCl donates a proton to water, and therefore, this will be the acid. This will be acting as a base because it accepts a proton, and H3O plus becomes conjugate acid, and Cl minus which is capable of accepting a proton will be a conjugate base. If you check, you can see they differ by a single proton. Now, take the case of acetic acid. Acetic acid, it donates a proton to water. You have H3O plus, again this will be the same as conjugate acid, and acetate ion will be the conjugate base, and here acetic acid acts as an acid and water acts as a base. Again, HCl when treated with ammonia which is a base, here this was neutral water, in this case we are going to take ammonia and you can find that HCl donates a proton to ammonia, it becomes NH4 plus and Cl minus is left out. This will be a conjugate acid and this will be a conjugate base, and HCl, since it donates a proton, that will be an acid, and ammonia will be the base because it accepts the proton. Again ammonia with water, which we have already seen. Here again ammonia accepts a proton from water, gets converted into NH4 plus and OH minus. And here all we can see that they are a pair. You can see from acid it gets converted into a conjugate base, okay. Base gets converted into a conjugate acid, that should be remembered. From acid you get a conjugate base. From base you get a conjugate acid, and these two differ by a proton. Okay. Now, let us see what do you mean by amphoteric substances or amphiprotic substances. A substance which can act as both acid and as a base. We call such substances to be amphiprotic. We have heard of amphibians which can live both in land as well as in water, just like that amphiprotic substances, or we call it as amphoteric substances, and here amphiprotic stands for proton. So, these are substances which can act as an acid and a base, or you can say that which can donate a proton as well as accept a proton. Such substances are known as amphoteric substances. Here let us take HCl. When treated with water, HCl donates a proton to water and you get H3O plus Cl minus, in which water acts as a base because it accepts a proton. Now, when we as we have seen already, that is when we take ammonia, water donates a proton to ammonia. Here water is acting as a acid because it is donating a proton, and you get ammonium ion and OH minus ion. Since water acts as an acid as well as base, water is an amphoteric substance. Hope it is clear. Here water accepts a proton and here water donates a proton, and therefore water can be considered as an amphoteric substance. There are many other substances, like they are usually ions, that is bicarbonate ions, bisulfate ions, all these act as amphoteric substances. Now, let us see relative strengths of acids and bases. What do you mean by relative strength? To what extent an acid can donate a proton determines the relative strength of an acid. And substances, for if you consider the bases, the extent to which a base can accept a proton depends on the strength of that base. Okay, how far it is ready to give a proton determines the strength of an acid, and how far an base can accept a proton determines its strength as a base. Now, let us take the case of two acids, that is, one is HCl, the other one is acetic acid. HCl donates a proton to water to give H3O plus and Cl minus. To what extent? That is what we have to see. We can see that in this case HCl has got more tendency to donate a proton to water, and the forward reaction takes place to a larger extent, while backward reaction to a smaller extent. That is, here water protonating the chloride ion to give back HCl, that will be very slow, while the forward reaction is to a greater extent. So, you can say that in this case HCl has got more tendency to donate a proton than the chloride ion accepting a proton and coming back as HCl. So, here the greater tendency of HCl determines that it is stronger acid. While when I take acetic acid and I put it in water, what happens is, of course, acetic acid donates a proton to water to get converted into H3O plus and acetate ion, but the reverse reaction occurs to a greater extent. That is, protonation of acetate ion and getting converted into acetic acid occurs to a greater extent, while the forward reaction to a smaller extent. What does it mean? The tendency of acetic acid to donate a proton is to a smaller extent when compared to that of HCl, and therefore we consider HCl to be a stronger acid than acetic acid. That is what we mean by relative strength of an acid. Now, there is one more case to explain this. Here, HCl donates a proton to water very readily, while chloride ion does not accept a proton to that extent to get converted into HCl. And what is Cl minus here? This is the conjugate base of HCl. Since conjugate base has got less tendency to accept a proton, or you can say that the conjugate base is a weak base because it has got a smaller tendency to accept the proton. Okay. And in that cases, you can say HCl is a strong acid just because its conjugate base is a weak. That is what it is mentioned here. If an acid is strong, its conjugate base will be weak, and vice versa. Again, here you can see that here acetic acid donates a proton to water to not that much extent, and therefore here acetate ion, which is ready to accept a proton, what is that? This is the conjugate base of that acid, but it is a strong base. It is ready to accept a proton, and therefore acetic acid is a weak. Now, when we take the case of a base, the same thing applies. If the base is strong, its conjugate acid will be weak, and vice versa. Okay. Next, let us see the proton transfer equilibria in other protonic solvents. Now, I am taking acetic acid. Here we have been seeing acetic acid in water. Instead of that, let us see acetic acid if taken in ammonia, which is a solvent. We know that ammonia is basic in nature. Acetic acid has difficulty to donate a proton to water because water is not that ready to accept a proton, while in this case ammonia being basic in nature, it readily accepts a proton from acetate ion to form ammonium ion, and acetate ion will be released. In this case, this acts as a strong acid because ammonia is ready to accept, it is waiting to get a proton, and therefore it accepts readily a proton from acetic acid than water accepting a proton, and therefore acetic acid, if I take in liquid ammonia, acts as a strong acid. Okay. In a similar way, the same acetic acid, if I am taking in hydrogen fluoride, what happens is hydrogen fluoride is a strong acid than acetic acid. So, instead of accepting a proton from acetic acid, hydrogen fluoride, what it does, it gives its proton to acetic acid, and therefore here acetic acid acts as a base. In the other case, it was a strong acid, but when I have taken the same acetic acid in hydrogen fluoride protonates acetic acid. You can see that CH3CO H2 with a positive sign and fluoride ion is formed. Here hydrogen fluoride acts as an acid. This is a solvent, but it acts as an acid. In a similar way, nitric acid, which is a strong acid in water, when I add that in hydrogen fluoride solvent, what happens is hydrogen fluoride protonates even this nitric acid. So, nitric acid shows basic nature in hydrogen fluoride. because hydrogen fluoride is a strong protonating substance and therefore it protonates nitric acid. You can see that nitric acid accepts a proton and fluoride ion is regenerated. So, depending upon the type of solvent you are taking, the acidic character varies. Now, let us go for the glacial acetic acid. Glacial acetic acid, so this is a solvent. Okay, when I add ammonia, which is a very weak base in aqueous solution or in water, you can see that this ammonia readily accepts a proton because that is basic in nature, and therefore acetic acid readily protonates ammonia and ammonia gives NH4 plus ion, or you can say that ammonia becomes a strong base when I take glacial acetic acid as the solvent. So, solvent also determines whether an acid will be a strong acid or a base will be a strong base. It determines by the nature of the solvent also. Now, let us see what are the advantages. It is applicable only to aqueous solutions, but to all protonic solvents. So, it is applicable to aqueous solutions, but also to all protonic solvents. So, in this case you can take aqueous solutions also and also to any protonic solvents. The concept is broader than Arrhenius concept because you can include more substances as acids and bases. It defines acids and bases on the tendency to donate or accept a proton, not as furnishing H plus ions or OH minus ions in aqueous solutions, that is according to the Arrhenius theory. Limitations is that it can explain in protonic solvents whether it is an acid or a base, but the defect is that it cannot explain the acid basis reactions in non-protonic solvents. That is, non-protonic solvents like liquid nitrogen dioxide, sulfur dioxide, carbon tetrachloride, in all those things, they do not have any protons, and in such cases it cannot explain whether a substance is an acid or a base. And also it can explain many acid base reactions which do not involve proton transfer. It cannot explain. Why? Because there should be a proton donation or acceptance to define a substance to be either an acid or a base. In this case, we do not have protons involved. Such acid base reactions cannot be defined based on this Lowry-Bronsted theory. Now, let us conclude. Here we have been seeing what is an acid and a base, a general concept, and we have been dealing with theories of acids and bases. We have been seeing two theories. One is the Arrhenius theory, in which we consider an acid to be a proton furnishing substance in aqueous media and base a substance which furnishes OH minus ions in the solutions. According to Lowry-Bronsted theory, proton is a substance that can donate a proton and base is a substance which can accept a proton. With that we conclude. Thank you.